Now, before I go into this, I thought I would discuss a little bit my journey towards discovering this. In 2000, I moved to Penn State. After teaching at the University of Michigan, I'd been teaching glacial and climate geology there. And I got a position, a research associate position at Penn State University, doing climatological and hydrological modeling. And it was August of 2000, and I was going to the #1 ranked climate research lab in the country, at least in terms of academic labs. And Al Gore was going to be in the White House, so life was set. Well, that didn't happen. So anyway, in the process of working there, though, I was reading the hydrogen economy. Hydrogen started becoming a popular topic around the turn of the millennium there, and a book by Jeremy Rifkin, The Hydrogen Economy, discussed how hydrogen could be used to store energy and could revolutionize the way we use energy. So in the book, there was an example of hydrogen being electrolyzed from water, and the hydrogen gas was stored on trucks, and the trucks were converted to run on gas, much like a truck can be converted to run on propane. So they had a fleet of trucks that they had hydrogen tanks in the back, and they were running off of hydrogen gas. So hydrogen became a big topic in 2002. Bush used it as a State of the Union address to talk about what he was doing for the energy problem, the energy issue, and clean energy issue that people wanted to know what was going on. So anyway, the Penn State, there were several universities that were competing to be centers, if you will, hydrogen research centers, and Penn State decided to have a hydrogen conference. I went to this conference to discuss the new topic, hydrogen, and particularly fuel cells. A fuel cell is a device that will take hydrogen and electrolyzes the hydrogen in a chamber with a membrane between the oxidizing and reducing cell, which enables the passage of the current, and you can then extract the energy from hydrogen electrolytically, create a electric current rather than heat. And so that's the idea is to use hydrogen fuel cells to make electricity to run an electric car. And in the course of this conference, somebody, engineering person, asked, why do we want to put so much emphasis on fuel cells? Why don't we just take the hydrogen and burn it in an ICE, an internal combustion engine? Why don't we use an ICE versus a fuel cell? We have 100 years of engineering in the automotive industry working with internal combustion engines. Why can't we just burn the hydrogen in a cylinder? And the answer to that question was because the burning hydrogen, even though the fuel is clean, produces heat, and that heat then oxidizes nitrogen in the atmosphere. So you get heat waste, of course, but you also get nitrogen oxide compounds, which I mentioned before, are acid precipitation forming. So a lot of the argument for using an electric car, and particularly an electric car with hydrogen, is to clean up emissions, particularly in cities. But I raised a different concern at this conference. I asked about freshwater demands, because in reading The Hydrogen Economy by Jeremy Rifkin, I discovered that the electrolysis, the hydrogen production that they did from water, was using fresh water. Looking at hydrogen production, 90% of the hydrogen is from steam reforming of natural gas. So that doesn't really solve anything with the climate change problem, because you're releasing CO2. You take natural gas, which you could produce from an oil field, and then you put it under steam. This is the the natural gas is a CH4. You put it under steam, the two water molecules there, and you drive off the hydrogen into the form of hydrogen gas, H2. But you create, in red there, a molecule of carbon dioxide. So you're producing hydrogen to use as a clean fuel, but you're still producing CO2 as if you were just burning natural gas. 90% of hydrogen on the market today is formed this way, the steam reforming process. So it's not really, hydrogen's not really a clean fuel. The clean alternative is to do electrolytic hydrogen, which is electrolysis of water, to split the water into the hydrogen and the oxygen separately. It takes energy to do that. It also requires fresh water. And I was concerned that this was going to set up a resource competition. I wrote an article the year following that conference discussing exactly that. It was just a short editorial in the journal Groundwater. But my quote, if I can quote myself here, everybody was raving about the fact that you have this hydrogen car and has clean fuel, and the only exhaust coming out the back of a hydrogen car is fresh water. People had actually been talking about making the LA basin into a rainforest from all the water exhaust. Well, couching that a little bit, the fresh water exiting a fuel cell from when you're reacting the hydrogen in the fuel cell to extract electricity is only fresh water because there's fresh water entering an electrolyzer to produce the hydrogen in the first place. So you take fresh water and you put it into the cell, and you electrolyze that fresh water into hydrogen. And then when you reuse the hydrogen, you produce water again. No surprise there. Well, why did the water have to be fresh water? Why couldn't we use salt water, use the ocean for doing hydrogen gas electrolytically from seawater? And well, the main reason is that when you electrolyze seawater, as you'll see, you produce other compounds. So that competes for the energy that you're trying to invest into the hydrogen from the water. But the other reason is that fresh water is required, if you will, to make a potassium hydroxide solution. The potassium hydroxide here is KOH. It turns out that if you do electrolysis with potassium hydroxide, you're producing hydrogen the most efficient, with the most efficiency. And I want to thank the folks at electrolyzer.com. Well, actually, they were Electrolyzer Corporation, then they became Stewart Energy, and now they're Hydrogenics. So, but in the past, when they were Electrolyzer.com, or Electrolyzer Corporation, I called them and was asking them about the solution, and was told about this electrolytic reaction involving potassium hydroxide. And it's pretty slick. You can see here that on the anode, with electrolysis, you're putting current into the anode, and that's the electrons are coming out, so that's oxidizing going on. So in that anode, you're producing oxygen there in red, and you're also producing acid, but that acid reacts with the potassium hydroxide and gets neutralized to water. And then in the cathode, where you're putting electrons into the system, you're producing the hydroxide back, as well as producing hydrogen gas. So out of the cathode cell, you're producing hydrogen gas, and out of the anode cell, you're producing oxygen. And the potassium hydroxide just recycles. Potassium hydroxide is recycled, and it makes for a very efficient electrolysis. But that requires fresh water to do that. So the next stage of this journey was, well, my position ended at Penn State due to lack of funding. Climate change lab kind of changed missions a little bit. No surprises there with the new administration. And I was interviewing in 2006 for a position at the Energy Research Institute, EPRI. And they were interested in my background in the Michigan Basin, geology. I've done some groundwater modeling there. And the Michigan Basin is of interest for sequestering, that is storing CO2 underground, because the Michigan Basin has ideal structure with the way the sedimentary rocks are bedded and the structures that are formed between shales and more permeable rocks to hold CO2 fluids. And also that it has a large amount of brine, and it turns out the CO2 is stored more readily in brine. So there's a number of reasons why the Michigan Basin has been considered for carbon sequestration by injecting the carbon dioxide underground. And in the course of that interview, I was informed that CO2 is not only an asphyxiant, meaning it not only drives out oxygen in an environment, making it so that you can't breathe from lack of oxygen, but at high concentrations, the CO2 itself is actually a lethal gas. And I remember being asked the question, would you be comfortable handling public relations aspects of, say, an underground injection proposal or an underground injection program for putting CO2 underground? And I didn't think I would feel very comfortable with that, so I didn't get that position. But anyway, the point that I'm trying to make here, though, is carbon sequestration processes are industrial. You're dealing with a gas that's an asphyxiant. In other words, it will replace oxygen. Coal miners had to worry about CO2 driving out the oxygen in their coal mine, and that the gas itself is not. It can be lethal, and the processes that we're using here to store it are industrial. They're not necessarily environmentally friendly. And it also, as we'll see, it takes energy in order to do something with the carbon, whether you're just collecting it and storing it underground, or whether you're going to do some kind of the mineralization process that I'm discussing. It takes energy to do that.